In this video, we will look at exponents. Before we get started, I just want to remind you on how to do mathematics. So number and copy the examples, ask your teacher if there are any steps that you do not understand, number the questions, and unless you have the ability to get fit while watching someone else run, you must do the questions on your own before watching the answer. So if the video says you must pause, you must first pause and do the answer on your own. Then mark your answers. If it is incorrect, write down the corrections. Make sure you understand where you went wrong. This will enable you to do better the next time you attempt a similar sum. Okay, so let's look at an overview on what we're going to be doing in this video. First, we're going to look at the laws of exponents. Then we're going to do a few revision sums that's based on the laws of the exponents. Then we're going to look at negative exponents, and then go on to more complex examples, then exponential equations, and then scientific notation. So let's get started with laws of exponents. Now, the very first law has to do with multiplication of the same basis. So that means if I have two bases that are identical and I multiply them, then I add my exponents. So for an example on that, I've got for A, I've got 2 to the power 3 times 2 to the power 2. So these bases are exactly the same. So therefore I can say 2, 3 plus 2. And that gives me 2 to the power of 5. And then I can work it out as 32. If it is a large number, then I can just leave it in exponential form. Then we go on to this one. Now here we've got two identical bases of A, so in this case I can just say it's A to the power of 3 plus 4, so I get A to the power of 7. And then for C, we've got 3 to the power of 5 plus 4, and then I get 3 to the power of 9. Now that I cannot work out without a calculator, so then I'm just going to leave my answer like that. Right, so let's look at the next law. The next law has to do with dividing the same base. So that means if I've got a base of A divided by a base of A, but with different exponents, not necessarily different exponents, but with the exponents can be different or the same, then I subtract my exponent. So let's look at an example. If I've got A, if I've got base of 3 to the power of 6 and base divided by base of 3 to the power of 2, then I can write it as 3 to the power of 6 minus 2. And that just simplifies to 3 to the power of 4. Now for B, here we have A to the power of 8 divided by A to the power of 3. So it just becomes A to the power of 8 minus 3. And that is equal to A to the power of 5. Next, we look at the law that has to do with raising a power to a power. And that means if I've got A to the power of m, and then that is again raised to a power of n, then I multiply my two exponents together. So let's look at a few examples. For example, A, I've got 5 to the power of 2, and then again to the power of 3. So that means I can simplify it by saying 5 2 times by 3. And that's equal to 5 to the power of 6. And for B, I've got A to the power of 4 to the power of 3. So A 4 times by 3 is equal to A to the power of 12. Right, so now the power of a product or a quotient. So this is much like our previous law, except now we have more than one basis in the brackets, and also if we have a fraction in the bracket. So if we have more than one base, this exponent needs to go to each and every base. So it will become A to the power of m times by b to the power of m. And similarly, if I have a fraction, this m has to go to all the bases inside these brackets or to the fraction. So let's look at these examples. I have xy to the power of 4, so that just simply becomes x4, y4, because the 4 goes to both bases. Then for B, we have a to the power of 5 over b to the power of 5. Once again, the 5 just went into both of the bases. And here we have a to the power of 5, y to the power of 3 to the power of 6. So once again, we go to both bases, but remember that law that says we have to multiply our exponents if it's a power to a power. So this becomes a to the power of 5 times 6, and then y to the power of 3 times 6. So this simplified then gives us a to the power of 30, y to the power of 18. Now we have the zero exponent law, and that basically says that anything to the power of 0 is equal to 1. So even 1,000 to the power of 0 is just equal to 1. And the only one that can't be equal to 0 is 0 itself, because 0 to the power of 0 is not defined. But any other number to the power of 0 is 1. Now let's look at these examples. So here we have 3 to the power of 0. Our answer is just 1. Even a negative number, as long as the negative number is in brackets, everything in brackets equals to 1. And here we have addition of two numbers, all of it, everything in this bracket, everything, because this bracket represents everything inside the brackets is up to the power of 0, so all of that is just equal to 1. Alright, so that was the laws. Now let's do some sums on it. Okay, so for question 1, let's start with A. Now in this question we have coefficients. So when we multiply this with this, we have to multiply the coefficients with each other, and that's just 2 times 5, so that becomes 10. And then a times by a, we add the exponent. So this becomes a 4 plus 3, and then this becomes 10 to the power of a, or 10a to the power of 7. Okay, now for b, over here we have the same base that's divided. So that means we subtract the exponent. So this is a 9 minus 5, and that is a to the power of 4. Then c, here we have once again multiplied and with coefficients. So this is then 4 times 5 gives me 20. Then m and m. Now this has an imaginary 1. If there's no exponent, it is to the power of 1. So if I have m and m, if I add my exponents, then I get 2 plus 1. And then for n, I have 3 plus 5. Right, so I can only add the exponents of the same basis, all right? And then I get 20 m to the power of 3 and n to the power of 8. For d, we have a power to a power, so this is m 6 times by 4, and this gives me m to the power of 24. Then for e, I have now, this is important because don't forget about this. That's one mistake that people tend to make. So this has to go to both of them. And then also, don't make the mistake of saying 3 times by 2. Remember, what is 3 squared? 3 squared means 3 times by 3, which is equal to 9. So if I say 3 squared k 4 times 2, then this will equal 9k to the power of 8. Alright, so these ones look a bit more complicated, although if you look at this one, you would actually, this looks exactly like, well, it's a fraction. So in fractions, what we'd normally do is we would cancel top and bottom, right? We would say cancel 6 of these a's with 6 at the top, then we're just left with a to the power of 3. Now, when you're busy with exponents, use your exponent laws rather. Especially when you're in a test, if you're writing a test on exponents, use the laws. So for example, let's just do this for example. If I have a to the power of 3 over a2, if I'm thinking about this in terms of fractions, then I'll say, okay, I'm going to cancel these two with 2 of these, and then I'm just left with a. But when I do it in terms of exponents, I'm going to say, I'm going to subtract my exponents, 3 minus 2, and that just gives me a to the power of 1, which is just a. So when you are busy with exponents, rather use your exponential laws because you can get marks for your steps. But if the test doesn't specify, then you're free to use any method. Alright, so In this case, the 36 and the 12, we still going to simplify it as we do with fractions. 12 can go into itself once and into 36 3 times. Then we have 3 over here, so this is F. We have 3 over here, and then A, 9 minus 6, so 9 minus 6. And then for B, we have 3 minus 3. And then for C, we just have C squared. Okay, so next step, I'm just going to simplify that. So A to the power of 3, B, 3 minus 3 gives me 0, and C squared. Then the only thing I still have left to do is this B to the power of 0. Remember, anything to the power of 0 is 1. So this just becomes 1, which means I just have 3A to the power of 3 C squared. For G, now if I look at this whole bracket is to the power of 1. So that means this whole bracket will, to the power of 0, this whole bracket is going to equal 1. Then times by, now this one, I have to take this 2 into each and every base. So this becomes 2 squared, A 5 times 2, and B 3 times 2. So times anything times by 1 is just that anything. So this, I can leave that out. And then 2 to the power of 2 is 4, A to the power of 10, and B to the power of 6. Then for H, we have just this part multiplied by this part. We've got these two coefficients to multiply, so 2 times 2, which gives us 4. And then K squared times K to the power of 9, so that's K2 plus 9. And M to the power of 1 times by M squared, that gives me M1 plus 2. So this is then 4, K to the power of 11, and M to the power of 3. Right, for I, there's these different terms. So remember your BODMAS in this case also. Where do your different terms lie? This is one term, this is one term, and that's one term. So that means simplify your individual terms first, because you have to multiply before you add. Now for this term over here, 4 to the power of 0, so that just gives me 1. Then I have plus, then 3 times negative. So what am I going to simplify first? This negative 2 to the power of 0, I can simplify first. That also just gives me 1. So this is then 3 times 1. And then plus, so in this case, we also have this that's equal to 1. So that's just 6 times 1. And then we get 1 plus 3 plus 6. And that gives us 10. Okay, so now for J, we have 18 x to the power of 6 times y to the power of 3 over 9 x to the power of 4 y times y. Okay, so when we look at this, this is also a fraction, so I can say 9 can go into itself once and into 18 2 times. This times this, it's just going to simplify to x to the power of 6 y to the power of 3 over x to the power of 4y. This is to the power of 1. So now I can go ahead and use my second law. So I'm going to say 2, then x to the power of 6 minus 4, and y to the power of 3 minus 1. So this is 2x to the power of 2 and y to the power of 2. Right, so that was the revision. Now let's look at negative exponents. So for this example, it says simplify the following expression and leave the answers with positive exponents. Okay, now before we get started, let's just look at how do we treat negative exponents. If I have x to the power of negative 1, what I do with it is I can put it over 1 because that makes it more clear actually. Then when I have an exponent that's negative, I take the base down, and then the sign changes of the exponent. So this is going to become then 1 over x to the power of positive 1. So let's look at something that looks like this. Let's say we've got 2 over y negative 2. So here we have a negative exponent. We want to make it positive. So I'm going to move my base up in this case. So this then is 2y squared. This is over 1, but we don't have to write over 1. So then I moved my base up and my exponent became positive. Right, so whenever you have a number that has a negative exponent, you just move it up or down depending where it lies and change the sign of the exponent. Okay, so here we know from the previous laws that in this case, power to power, we just multiply this. So this is going to be 3 times 2, which is 6. Now this is a negative exponent, so I'm going to move my base down and change the sign of my exponent. So this is going to become 1 over 8 to the power of 12, and then times by 8 to the power of 4. Okay, so just to get all of this together, let's put it over one fraction. If I put this over 1, then multiplying all this together would give me a to the power of 6, a to the power of 4, because they're in the numerators, and then over a to the power of 12. Okay, so now the law that says if I add my multiply same basis, I add the exponent, so this would then give me a to the power of 10 over a to the power of 12, and now I divide my same basis, and then I get a to the power of 10 minus 12. So this gives me a to the power of negative 2, which again gives me a negative exponent, so I'm going to make it positive by saying 1 over a to the power of 2. Alright, so we changed this immediately, but a different thing that we could have done, which might have been easier actually, is to just add your exponents as they are, even if they're negative. So if we're at this point, I'm just going to write it down here. So if we just change, or we just simplify this part, you'd get a to the power of 6 times by a to the power of negative 12 times by a to the power of 4. Then you just add your exponent, so that's 6 minus 12 plus 4, and that would also give you a to the power of minus 2, which you then just change into a 1 over a to the power of 2. So you don't necessarily have to immediately make your exponents positive. You can actually just do your calculations, but at the end it says you have to give your answer with positive exponent, so that's where it is very important to change it to a positive exponent. Okay, so let's simplify this expression. So here we have 5 times by negative 3 in brackets with a negative 2. So what's very important is that only the base that belongs to the exponent gets moved down. So I've seen this a lot where we have 7a minus 2. Then the answer, which is wrong, but what a lot of people do is they'd say this is 1 over 7a squared. This exponent only belongs to this a. So it's only, so this is wrong. What would have happened is that, what should happen is that the 7 stays at the top, only the a, which belongs to the exponent, goes down and the exponent becomes positive. The only scenario where the 7 might also go is if we had 7a and then in brackets minus 2. So then everything in the brackets belong to the exponent, so then we have 1 over 7a to the power of positive 2. Okay, so in this case, it's important that only the negative 3 moves down. So here we have 5 staying at the top, and then negative 3 comes down, and the exponent is positive. Keep its brackets there. Because of this negative, it's important to keep the brackets there, because if you don't have the brackets, if I say negative 3 squared, then my answer is negative 9. But with the brackets, the answer is positive 9, because this square makes that minus a positive. And you can even test this on your calculator. If you type it in like this, you'll get negative 9, but if you type it in with the brackets, you'll get positive 9. So that makes a difference. Okay, and then we have 5 over 9. Okay, so let's simplify this expression. So here we have all of this belonging to the exponent, so all of this can go up. So this is then a plus b. We can keep it in brackets, although this is just to the power of 1 now, so this is just going to be a plus b. We can drop the brackets there. Then here we have plus 2 times by, now all of this becomes 1. because it's to the power of 0, minus, now how do we simplify this? We're going to multiply in the minus into the brackets. So this becomes minus a minus b. So this sum, if you look at it like for the first time, it really looks big and complicated, but it's actually just a few smaller sums broken up. So if you always think of sums also like breaking them up into their different terms. Then you simplify the different terms first, and then you add and subtract. So you know how to do this little part over here, then you just do this little part over here, and then just this little part over here. And then once we've simplified that, we can go on. Now this is just a plus b plus, this becomes 2 minus a minus b. So a minus a is 0, b minus b is 0, so our final answer is just 2. Okay, so example 2.4, we have a minus 3 5 over b to the power of negative 6. So I'm not going to change my negatives or my exponents to positive exponents. I'm just going to do the calculations as I know them, and then I will make them positive. Alright, so this one is just going to be a negative 3 times by 5, and that's over b to the power of negative 6. And then I have a to the power of negative 15 over b to the power of negative 6. So now I cannot take this any further. We don't have the same base here, so we can't divide them by subtracting the exponents. And now I'm going to take all my exponents and make them positive. So a must go down and b must go up. So this is then a to the b to the power of 6 over a to the power of positive 15. Okay, so now simplify this expression. We've got x to the power of 8 over 6, x to the power of negative 2. Alright, so once again, let's do it by just doing the calculations as we know them. So I'm going to say that x, 8, now very careful here, this is another common mistake. When I subtract a negative number, so I need to subtract negative 2. A lot of people will just say, what is 8, or the 8 minus 2. But remember, you're saying 8 minus negative 2. So what are we going to actually say is it's going to become 8 plus 2 over 6. So this is then x to the power of 10 over 6. Okay, now we simplify this expression. So here we have a to the power of negative 5. So these guys get times together. So we have b minus 4 times minus 2 gives me a positive 8 over b to the power of negative 3. And now the same bases are these b's over here. So I've got a to the power of negative 5, then b 8 minus negative 3. And this gives me a to the power of negative 5, and b 8 plus 3 is going to be 11. And then I can just change this guy's exponent into positive by taking the a down. So I have b to the power of 11 over a to the power of 5. Okay, and then for this expression, now this one has a lot to do with signs. Although let's start by making this exponent positive, because if this is over 1, then I can take this whole base down. So this will then become 1 over negative 3 to the power of 3. Okay, so now signs. When I square a negative number, it becomes a positive number. But when I take the cube of a negative number, it stays a negative number. And that is because minus 1 times minus 1, that's the same as squared. A minus and a minus gives me a plus. But if I say minus 1 times minus 1 times minus 1, then these two together becomes plus, but then that times by the negative again gives me a negative, because a plus and a minus is a negative. That's why all the negative numbers squared gives you a positive number, and all the negative numbers cubed gives you a negative number. So in this case, if I know 3 cubed is 27, then negative 3 cubed will be 1 over negative 27. Okay, and then this expression. Now, what I would like to do, or what I like to do actually, when I have a negative exponent inside and there's fractions inside, and that's just something that it's up to you if you want to do it, but I like to immediately make this positive by just flipping everything on the inside around. Even if there's more, like if it was AB over CD to the power of negative 1, to make that positive immediately, you just flip everybody around. So then it becomes CD over AB. So in this case, I'm going to say I've got 5 over 3 to the power of 2. And then I'm going to take my 2 to all the bases, and I have 5 squared, which is 25, and over 3 squared, which is 9. And that's my answer. You can, if you want to, rather say this becomes 3 to the power of negative 2 over 3 to the power of negative 5 to the power of negative 2. Then swap them around, like making this positive, taking your 5 up. 5 squared over 3 squared, bringing the 3 down, and then getting 25 over 9. That's just what you prefer to do. Now, question 2 says, simplify and express each of the following expressions with positive exponents. So if I look at A, and I have 4a to the power of negative 2, then to make this exponent positive, I'm going to move a down, and only the base of a, so then I'll get 4 over a squared. Then for B, I've got x to the power of negative 4, y to the power of 5. So to make this one positive, I'm going to say y to the power of 5 and move the base of x down, and then the 4 will become positive. Then for C, I'm going to do the same, where I'm going to take the base of 5 down. So then I have 3 over 5 to the power of positive 2. And then to simplify that even further, I've got 3 over 25. For D, over here, we've got 2x, but it's in brackets. So that means this negative 3 belongs to both, or these bases both belong to the negative 3. So that means this entire bracket is going to move up. So we have 2x and then with a positive 3 over 1, but we can just now write it like that. And then to simplify it further, I need to take the 3 inside, and this will then give me 2 to the power of 3, x to the power of 3, because the 3 has to go to all the bases. And then it is equal to 8x to the power of 3. Then for E, now both of these bases have negative exponents, so the A is coming down and the C is going up. So this is going to be C to the power of 5 over A to the power of positive 3. Then for F, we have all of these have negative exponents. So that means this guy needs to go down, y needs to go up, z needs to go up. And then I have y to the power of 7, z to the power of 2, and x to the power of positive 4. Then for G, so here we have a to the power of 0. So remember, anything to the power of 0, that's 1. So this whole thing is going to change into 1. And then we have plus, and this 5 has a negative exponent of minus 1. So that goes up, and it becomes 5 to the power of positive 1. Over 1, but we don't have to write over 1, and we also don't have to write to the power of 1. So this is just 1 plus 5, and then we have 6. Then for H, over here we have all of this in brackets, this negative 2. So if I put it over 1 and I want to make this exponent positive, I'm going to take my base down. Then I have 1 over negative 2 in brackets, but with a positive exponent. Then if I square a negative number, it becomes a positive number. So this is going to be 1 over positive 4. For I, Both these bases have negative exponents, so the 3 goes down, 4 goes up, and I have 4 squared at the top and 3 to the power 3 at the bottom. Then 4 squared is 16 and 3 to the power 3 is 27. Then for J, now if I have a fraction inside a bracket with a negative exponent, all that you do is the whole fraction you just flip around. So this is going to be, instead of 2 over 3, I write 3 over 2. So that's going to be with a positive exponent 1, but we don't have to write exponent of 1, so we just simplify it as 3 over 2. For K, I have, okay, so in this case, this looks very long, but I'm just going to take it one term at a time. So if I break this up into its different terms, remember a term is separated by a plus and minus sign. For my first term, I simply have 5 to the power of 0, and that's equal to 1. Then that's plus 5 to the power of 2, that gives me 25. Then I have 5 to the power of negative 1, so that is 1 over 5. And then we have a negative 5 to the power of negative 1, so this one has to go up. That becomes 5 to the power of positive 1, and this is then plus just 5, and then minus 5. Alright, so if I now look at this, we have 1 plus 25, so this gives us 26 plus 1 over 5, and then plus 5 minus 5, so this gives me 0. So this is now my answer, so then I can just simplify that by saying this is 26 and 1 over 5. Then for L, I have these two multiply together, but before I can multiply them, I have to simplify my square first. So, and we can see that this is a negative exponent, so this bracket needs to move down if I put this over 1. So if I move it down, I've got negative 2a squared at the top, and I don't have to put my brackets there anymore because this factor has now been moved down. So we have 2a at the bottom to the power of positive 2. Now when I simplify this, I've got my negative 2a squared here, and then this square needs to go inside, so that becomes 4a squared, and then we can start by, or simplify by cancelling. These a squareds can cancel out, but actually we are busy with exponents, so let's use the exponential law just to show how that works. But we do cancel 2 goes into itself once and into 4 twice, so here we'll still have 1 over 2, negative 1 over 2, but this a, if I use law 2, I've got a 2 minus 2, because divide by same basis, subtract your exponent, so 2 minus 2. Then it simplifies to negative a over 2, but this a has a power of 0 because 2 minus 2 is 0, and anything to the power of 0 is just 1. So my final answer is then minus 1 over 2, which is the same as just cancelling them top and bottom one. But like I said, when we work with exponents, rather use your exponential laws in your steps. Alright, so now that was L. Now for M, here we have t as our common base. All of these bases are equal to t, so I can actually just go ahead and use the first law where I just add my exponents. So I'm going to say I've got t where I've got negative 4 plus 5 minus 3, and then I add them, so this is equal to t to the power of minus 4 plus 5 is 1 minus 3, so that's negative 2. Then just to end off, I need to make my exponent positive, so I'm going to take the base down, so this is 1 over t squared. Then for n, we have x to the power of negative 3 to the power of 4. So this is the third law where if we have a power to a power, we multiply the exponent, so this then becomes x to the power of negative 12, and to make my exponent positive, I'm going to write it as 1 over x to the power of positive 12. And then O, Now I've got this base having a negative exponent, so it's only that x that goes down, and then this one going up. Now I have 5y to the power of positive 4 over x to the power of positive 3. Okay, so for p, we have t, so this base needs to go down, and then also this base. But now before we take it down, actually let's just simplify this first before we change the exponents at this point. So to simplify this part, we've got a power to power, so we have to multiply these exponents together. So I have t to the power of negative 4 times by t to the power of negative 6. And now let's just simplify it by multiplying them. We have t, or adding the same, or adding the exponent. So we have negative 4 minus 6. So this gives me t to the power of negative 10. And then I can take the t down and make it a positive. So this is then 1 over t to the power of 10. Now that was one method. The other method would be to immediately take the t down, and we can take this one also down. Then you'll just have 1 over t to the power of 4 t to the power of 3 with a positive 2. And then you follow those same steps, but then it would just end up already positive. Alright, so now for q. So the first thing I'm going to do is to simplify this by multiplying in my 2. So I have m to the power of negative 6 over m to the power of negative 4. Alright, so we can now do one of two things. Let's actually just use our law where we subtract the exponents. We have m minus 6 minus a negative 4. Okay, so whatever you see here, you subtract with whatever you see here. So to simplify this, I have m minus 6. Now a minus and a minus gives me a plus, so this becomes m to the power of negative 6 plus 4, and then I get m to the power of negative 2, and then to make my exponent positive, I'm going to write it as 1 over m squared. Then for r, so once again, just going to apply my laws by simplifying this one first. Actually, I can do two things in one step. I'm going to add my exponents of these same bases for the numerator, and then in the same step I'm going to multiply out this bracket in the denominator. So I'm basically just simplifying the numerator and denominator in one step, where I say for my numerator x, and then 5 minus 4, I add my exponents, over x to the power of negative 6. So this gives me x to the power of 1 over x to the power of negative 6. Then I have the same basis that's divided, so now I subtract my exponents. I have x to the power of 1 minus negative 6, and that becomes x to the power of 1 plus 6, which then gives me x to the power of positive 7. And then we have s. Now over here we have 3 times b to the power of 6 times by this times by b to the power of 3. So the first thing I'm going to do is to simplify this by taking out the bracket. So I have 3 to the power of b to the power of 6 times by b to the power of negative 10 when I multiply my exponents, times by b to the power of 3. So now to simplify these with the same bases, we add our exponents. So we have 3b6 minus 10 plus 3, and then we have 3, so minus 4 plus 3 gives me b to the power of negative 1. And to put that as a or make my answer with positive, give my answer in positive exponents, this base just needs to go down to make my exponent positive. So I have 3 over b to the power of positive 1, but I don't have to write to the power of 1. Alright, so then for t, so here all our bases are y. The first thing I'm going to simplify is just this one with the brackets where I multiply my exponents. Then I have y to the power of negative 3 times y to the power of negative 10 times y to the power of 50. And then I add my exponents because my bases are being multiplied. So I have y negative 3 minus 10 plus 15. So this is negative 13 and that's plus 15. So minus 13 plus 15, or we can say 15 minus 13, that gives us 2. So our answer is just y squared. Okay, so that was quite a lot of sums on negative exponents. So now we move over and we look at a few more complex examples. Okay, so example 3.1 says simplify the following expression giving the answers with positive exponents. So once again, we're just going to start and simplify this part over here with the brackets first. Then we get 8 x to the power of negative 2 y to the power of negative 10 x to the power of 4 over x to the power of negative 3. The next thing I can do is to simplify my numerator where I have this base of x and this base of x, which is multiplied together, so I can add my exponents there. This gives me 8 x to the power of minus 2 plus 4 gives me 2, and then y to the power of negative 10 over x to the power of negative 3. The next thing I want to do is when I have my same basis here that's divided, I can subtract my exponents. So I have 8 to the power of x. So now put in this step, especially because we have a negative exponent here that we have to subtract, you have to say 2 minus the negative 3. And then y to the power of negative 10. So this is then 8x 2, this becomes 2 plus 3, which then becomes 5. So to just finalize this one simplifies to x to the power of 5, and this one has a negative exponent which we need to make positive by taking the base down. So we have 8x to the power of 5 over y to the power of positive 10. So for example 3.2, evaluate the following. So over here we have okay, so with this one, this 15, if you have a large number with an exponent, the first thing you want to do is to write it in its prime factors. So if I write 15 in its prime factors is 3 times 5. So what I'm going to do is we're still going to just write 3 to the power 4 times 5 to the power 3 over. Then I'm going to replace 15 with 3 times 5 squared. Then I can take this 2 into every base, or to each base, which means I've got 3 to the power 4 times 5 to the power 3 still, and then that becomes 3 to the power of 2 times 5 to the power of 2. Okay, so first step was if you have a big number and you're working with exponents, first thing you want to think about is prime factors, breaking it up into prime factors, and then once we have its prime factors inside a bracket with a power, we know we have to multiply the power into each base, and then now we have 2 bases of 3 and we've got 2 bases of 5. Now they are divided, which means we can subtract our exponents. So we have 3, 4 minus 2, and then times by 5, 3 minus 2. This gives us 3 squared times by 5 to the power 3 minus 2, so that gives us 5 to the power of 1 basically, which then this becomes 9 times 5, and that's just equal to 45. So exponents actually enable you to simplify really complex sums without a calculator. So this is actually, exponents is actually a really great tool if you don't have a calculator. Okay, so for question 3, we once again have to simplify these expressions and express your answer with positive exponents. Now for A, I've got this, and all of this is in brackets, and it's to the power of negative 1. So that means this whole thing that's in brackets is to the power of a negative exponent. So I'm going to take this whole thing is the base of minus 1. So this whole thing needs to go down. So we have 1 over 2 to the power of negative 1, a to the power of 3. And that's all to the power of 1. But once again, I don't have to write that. Then when I look at it as it is now, we have this 2 to the power of negative 1. So now I want to make this positive by taking my 2 back up. So this is then 2 to the power of positive 1 over a to the power of 3. For b, over here, the first thing I need to do is to simplify the brackets by taking the 2 inside to each and every base. I've got 3 over a to the power of 3 times by 2, so that's 6. And b to the power of negative 2 times by 2 gives me negative 4. Now I need to simplify this by taking the b up, or make the exponent positive. Then we have 3b to the power of 4 over a to the power of 6. C. Okay, so here I've got bases of k, m, and t, and they are all divided, so meaning I can just simplify that by subtracting my exponent. So let's start with k. K is 3 minus negative 1, so that's 3 minus negative 1. Then I've got m. M is negative 5 minus 2, and t is 8 minus negative 3. So this is then k to the power of 3 plus 1. M is minus 5 minus another 2 gives me minus 7. And t is 8 plus 3. And then I have k to the power of 4, m to the power of negative 7, and t to the power of 11. Okay, so the only thing that's still left to do is to make this exponent positive. So I'm going to take my m down, and then I have k to the power of 4, t to the power of 11 over m to the power of 7. Right, d. Once again, I've got brackets. My exponent's positive, so I can just go ahead and multiply it into each and every base. I've got 3 to the power of 3, m to the power of, so negative 3 times 3 gives me negative 9, and n to the power of 4 times 3, which is 12. So this then is equal to, this becomes 27, and then I can take this one down by making the exponent positive. So this is 27 n to the power of 12, and then over m to the power of positive 9. For e, I've got 12 x to the power of 3, y to the power of negative 5, and then I've got all of this also to the power of negative 1. Now normally we'd simplify this by taking the exponent into every base, but this is going to make it actually a lot more complicated, because if I have a 2 here and I put it to the power of negative 1, this is going to give me a half, and then it's just going to be a fraction of a fraction, which is just going to complicate matters for me. So what I'm going to do here is just to take this base down, and this whole base which belongs to negative 1, I'm going to take that up. What I have then is 12 x to the power of 3 times by this 2x to the power of 4y to the power of positive 1, but I don't have to write that, and that's over y to the power of negative 5. Sorry, that becomes a plus 5. So now to multiply these two out, like if I put brackets here, multiplying this and this out, this is the coefficient, so 2 times 12 is 24, and then x to the power of 3 times x to the power of 4, that's x to the power of 7 when I add my exponents, and then I have y to the power of 1 over y to the power of 5. So now these bases of y gets divided, so we subtract the exponents. That means we've got 24 x to the power of 7, then y to the power of 1 minus 5. So this gives me 24 x to the power of 7, y to the power of negative 4. Then this this guy goes down to make that negative 4 a positive. So this is then 24 x to the power of 7 over y to the power of 4. For f, I have this 2 over here, so that we can just go ahead and take to each and every base inside the brackets. This becomes 3 squared, 8 to the power of, now when we take it in, we times the exponent, so that's 5 times 2, which is 10, b to the power of negative 8 over c to the power of negative 14. Right, and then we can just flip the ones up or down which have negative exponents, so that gives us, oh, and this I can change to 9, so this is going to be 9a to the power of 10. The c goes up, so that's c to the power of 14 over b to the power of 8. Okay, so that was the more complex examples. Let's look at some exponential equations. So when we're working with exponents, or actually exponential equations, what we want to aim for is to get one term equal to one term, and both these bases need to be identical, because if these bases are identical, that means that if these two terms are equal to each other and our bases are identical, that means that whatever is in the exponent, the exponents will then be equal. So if you are at this stage where you have one term equal to one term and you have the same basis, then we can say x is equal to 4, or this one's exponent will be equal to this one's exponent. So this was a very, very easy example, because normally, or a bit harder sums, we first have to manipulate our equation to get it to be the same base equal to the same base. So for example, in this example 4.2, we can see that we have 2 to the power of x equal to 8. Now, we need to try and get the same basis. Now, we know 2 is actually, 8 is actually equal to 2 to the power of 3. So here we have the same basis. So now I can say, therefore, x will be equal to 3. Then in this example, so here we have a fraction, but this is now 1 over 25. So in my case, I know 25 is 5 to the power of 2. So 5 to the power of x is equal to 1 over 5 to the power of 2. And this base actually gives you an indication of what this one needs to change to. Most of the time it will be this base, a power of this base. So now that we have 5 to the power of 2 here, we still have one problem. We need both our bases to be at the top. So in this case, we can just take our base up and change the sign of the exponent. So here we're going to say 5 to the power of x equals to 5 to the power of negative 2. And then we can say, therefore, x is equal to negative 2. Over here, we have 7 to the power of x minus 3 equals to 49. So 49 is 7 squared. So I can write 7 x to the power of negative 3. 7 to the power of x minus 3 equals to 7 squared. Now you can see this one's exponent is slightly more complicated than the previous examples, but that doesn't matter. We still have our bases being identical, so we can say therefore x minus 3 equals to 2. So whatever is in the exponent you just write, or you just equal to each other. So now we can solve for this simple linear equation, where we start by taking the 3 over to the other side. So I have x equals to 2 plus 3. When I take it to the other side, it changes sign. So x is equal to 5. Then we have the following. So now you have to remember that law that says anything to the power of 0 is 1. So if I have a 1, I can actually change this 1 into anything to the power of 0. I can change it into 99 to the power of 0. I can change 1 into x to the power of 0. I can change 1 into in our case, what do we have here? We've got a base of 6, so we want a base of 6. So I'm going to change it to 6 to the power of 0. So here I have 6 to the power of x equals to 6 to the power of 0, and therefore x is equal to 0. Okay, so for question 4a, solve the following equations. So I have 13 to the power of x minus 5 equals to 13 to the power of 4. Now both my bases are 13, so I can therefore just go ahead and say x minus 5 equals to 4. Then solve for x by taking my 5 over to the other side. So x is equal to 4 plus 5, x is equal to 9. Then b, I've got 3 to the power of x equal to 27. Now 27 is the same as 3 to the power of 3. So therefore x is equal to 3. And over here we've got 7 to the power of x equals to 1 over 49. So 49 is the same as 7 squared. So this is then 7 to the power of x equals to 1 over 7 squared. So this base I need to take up. Then I have 7 to the power of x equals to 7 to the power of negative 2. When I take the base up, exponent changes sign. So same basis, we can therefore say x is equal to negative 2. Right, for D, I've got a base of 5 over here, and here we have 25, so I can change that 25 into 5 squared. I've got 5 to the power of x minus 8 equal to 5 squared. So therefore I can say x minus 8 is equal to 2, and take my 8 over to the other side. This gives me 2 plus 8, and then x is equal to 10. For E, I've got a base of 5, and here I've got a 25 again. So once again, I'm going to change my 25 into 5 squared. Then I have x to the power of, I've got 5 to the power of x minus 6 equal to 1 over 5 squared. Take my base up. I've got 5 to the power of x minus 6 equal to 5 to the power of negative 2. Then drop my bases. Therefore, x minus 6 equals to negative 2. Take the 6 over to the other side. So x is equal to minus 2 plus 6. So x is equal to 4. Alright, that was the equations. And finally, let's do some scientific notation. Now, in this example, it says write this number in scientific notation. And in scientific notation is used when we work with very large numbers. Like in astronomy, when they measure the distances of stars and galaxies, they use very large numbers, and then when they use scientific notation so that the calculations are much easier. Or when you work with atoms and you use very small numbers, you can also write it in scientific notation to make your calculations much simpler. So when we have to write a number in scientific notation, you want to put the comma after the first number. That's where your comma needs to be always. So now you need to move your comma. So if we move our comma back, if it's a big number, your you have to divide by either 10, 100 or 1,000, but we write 10 just as 10, but 10 to the power of 2, that's equal to 100. 10 to the power of 3, that's equal to 1,000, and so on. 10 to the power of 4 is equal to 10,000. So when I move my comma back, I can rewrite this as 6,8954. So now I just put my comma here, and I can say times by 10 to the power. Now how many times did I move it? I moved it 1, 2, 3 times. So then I put a positive 3 there. Okay, so that means if I take this, if I multiply my new number with 10 to the power 3, remember when you multiply with 1,000, you shift your comma to the right. When you divide, you go to the left. Now, you can always double check to take your final answer. Would I then get back to that original answer? So this is in scientific notation. It's important that your comma is after the first number. Okay, so here we have a small number. Now, when I have a small number, once again, I want my comma after the first number. So I know this is going to be 8,500. 529, but then I say times by 10 again, but I've shifted my comma 2 places forward. So if you have a small number, your exponent here must be a negative. So then you have minus 2. Okay, so the best way to remember is if you have a big number that you wrote in scientific notation, your exponent here is positive. If you have a small number, your exponent is negative. And the reason for that is if I want to get back to that number, I need to divide by 100. So if I remember, we said 10 to the power of 2 is 100. So if I have 10 to the power of negative 2, this is equal to 1 over 10 to the power of positive 2. Remember, if I take my base down, I make my exponent positive, which is equal to 1 over 100, which is just the same as saying divide by 100. So that's why we have this negative exponent. Okay, so now we have a really, really small number. And to write that in scientific notation, I have to put my comma after my first number. So that's 6,79 and times by. So now I'm just going to check 1, 2, 3, 4, 5, 6. So it has to be 6 spaces, but remember this is a small number, so I put a negative. Okay, now example 5.4. Here we have a big number, and to write that into scientific notation, I put my comma after my first number, so it's 7,98 times by 10. So how many spaces? So remember, if you just have a number, like for example 789, then if it's just a number, the comma automatically falls there. So we don't write 789,000. Those are just placeholders. So normally we just write our number as this, but we always know there is a comma after the 9 with a 0 that follows. Zeros, the decimal places. So when we start with a number without a comma, the comma is always at the end. So taking the comma back, we move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. So this is a positive 11 because it's a big number. Okay, and then we have another small number, so I want my comma there. So I have 1,45 times by 10 to the power of, so if I move my comma 1, 2 spaces, then it's negative 2 because we're working with a small number. Alright, now without the use of a calculator, write this in scientific notation. So the first thing I'm going to do is I'm going to use my exponential laws to simplify these. You see, these are the same basis. 10 to the base of 10 to the power of 5. So I can just say same basis, add my exponent. So this is then equal to 65 times by 10 to the power of 5 minus 2, which gives me 3. But we're still not at the end yet, because with scientific notation you always want your comma to be after the first number. So if we just look at this part here, if we were just given 65 and say write that in scientific notation, what would we do? We'd say, okay, I want my comma there, so my comma is after the 5 for 65, so I'm going to say 6,5 times it by 10 to the power of 1, because I've moved my comma 1 back, times by 10 to the power of 3 for that part. So now just to simplify it even further, I can just say my same basis, so add my exponent, so I have 6,5 times 10 to the power of 4. Okay, now without the use of a calculator, write the following in scientific notation. So over here, I've got 24 times 10 to the power of negative 7 times 2. So in this case, these two are friends because they're the numbers. So 24 times 2 gives me 48 times by 10 to the power of negative 7. And then I just want, so let's just focus on the 48. The comma lies after the 8, but I want the comma to be after the 4. So I write 4,8. And since it's a bigger number that I made smaller, I'm going to say times by 10 to the power of positive 1. Then times by the 10 to the power of negative 7. And then I can just add my exponents here to simplify that. So 4,8 times by 10 to the power of 1 minus 7 gives me negative 6. Now for this example, here we have this 0,5 0.06 times by this 3, all right? So that's the first part where we have our number times by 10 to the power of something. So this has to be multiplied together. But before we do that, let's first change. Actually, no, let's multiply them out. So if I have, or actually no, let's first change it, because then the multiplication is easier. If I have 0.06, I'm going to say I want my comma to be after the 6. So I have 6 times by 10 to the power of, now this is a small number and I moved my comma 2 places, so I'm going to say minus 2 times by 10 to the power of 4 times by 3 times by 10 to the power of negative 5. So in the next step, I can say 6 times 3, which is going to give me 18. I can also simplify my bases along. So I've got 10 to the power of negative 2 plus 4 minus 5. So minus 2 plus 4 gives me 2, minus another 5 gives me negative 3. Okay, so we're almost there. All that we now need to do is just to get our comma after the 1. So if I have 1,8 times by 10, so this was a big number, then I moved my comma back once, so that's the positive 1 times by 10 to the power of negative 3. Then simplifying these two together, I get 1,8 times by 10 to the power of negative 2. This example is slightly harder because if you notice, there is a plus here. So that means we need to take this term and add it to this term. And the only way we can add these two is if this exponent is the same as this exponent. And I'll show you now in a small or in a moment. Before I show you why, I'm just going to first change one of these exponents into the other. And to do that, what I personally believe is it's easier to change the bigger one, the minus 2 into minus 3, because then we can take this. If I change minus 2 into minus 3, I move my comma right, to the right. So then it's 12 times 10 to the power of minus 3. If I change this one into minus 2, I have to move my comma back, which means I've got a more complicated fraction, decimal to work with, where then this would become minus 2. So what I'm going to do is I'm going to rewrite this as 12 times by 10 to the power of negative 3 plus 2,5 times by 10 to the power of negative 3. Now, here is why we need to change, we need to make this part identical to this part. So let's imagine that this is, or let's replace this with x and this with x. Then I can say, so I'm just going to do this at the side just to show you. Then I can say I've got 12x plus 2,5x. And because these are both x, they are like terms. So then I can add them. And I would simply get 14,5x. So in our case, we'd have, if I add these, I'd just get 14,5, and then in place of x times by 10 to the power of negative 3. So this can say in standard form or in exponential form. In standard form, it's quite easy because we're just going to then multiply it with this x to the power of negative 10 and take the comma back. But just back to that point I was making, if this is still a negative 2 and that's still a negative 3, then this isn't the same number. So that means that the one we can say is x and the other one y. We can't say they're both x because they're not the same number. So then you'd have 1,2x plus 2,5y. And we can't add these two because they're not like terms. And that's the same with this at the top. You can't add them when one exponent is equal to minus 2 and another one is equal to negative 3 because they're not like terms. So first change them. Okay, so and in doing that, we took the bigger one and we made the bigger, because minus 2 is bigger than minus 3, we made the bigger one equal to the smaller one, and then just multiply the 1.2 by how much we needed to change it. In this case, we just needed to shift it one place. So we just multiplied it with 10 basically. All right, but now it says in standard form, and in standard form, we get rid of this 10 to the power of whatever. And in our case, if we times by a negative number or a negative 10 to the power of negative exponent, that means our comma moved back. So I'm just going to put a few placeholders here as zeros, and I'm going to move my comma 3 places back. So that's 1, 2, 3. So my comma is lying there. So my final answer is 0,0145. Okay, so for question 5, we have to write these numbers in standard form. So if I multiply by a 10 to the power of a positive exponent, I move my comma forward 2 places. So this will then just be 634,7. And then for B, I've got a negative exponent, so let's just write this one here, because I want a few just placeholders, 1,932, because if you put in these placeholders, it's just easier to move your comma, and we need to move it back 3 spaces. So we say 1, 2, 3. So my comma is lying there, and I have 0,001932. For C, it's once again a negative number, so I'm going to put my few placeholders there, 0, 2, 3, 4. So moving my comma back 2 spaces, I've got 1, 2, so my comma is there. So I have 0,000, there's 3 zeros, 2, 3, 4. And then D, here I have to multiply with 10 to the power of a positive number. So now I'm just going to put a place. So I'm going to write this, 7300, because zeros after the decimal place that doesn't change the value, and zeros before your numbers of the decimal place doesn't change the value. So all of this doesn't change the value, and zeros after the decimal place doesn't change the value. So moving my comma 4 places forward, I have 1, 2, 3, 4. So I have 12573. So 12573. That's my number in standard form. Okay, so this we need to write in scientific notation. So first thing I need to do is put my comma after my first number, so that's 6,45, times by, and then 1, 2, 3. So I moved it 3 places, but it's a small number, so I have to say minus 3. That was E. Then for F, I've got a big number, so I want to put my comma there. So I've got 7,86452. And I moved 1, 2, 3, 4, 5, 6, 7, 8, 9. So I times 10 to the power of positive 9 because it's a big number. Then G, very small number, I want my comma there. So I write 6,92. And I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So times by 10 to the power of negative 10 because it's a small number. So H, 7,13 times by 1, 2, 3, 4, 5. So 10 to the power of negative 5. Right, so for I, we need to write this in scientific notation, and this is one of the hard sums where we have to add these. Before we can add it, we have to change these two exponents into identical exponents. So remember, which one do we change? We change the bigger one. So between minus 6 and minus 4, which is the bigger? Minus 4 is bigger than minus 6 because that's more negative. Minus 6 is more negative than minus 4. All right. So what I do is I need to get to minus 6, I need to subtract another 2. So that means I'm going to add 2 zeros here. So to rewrite this, I'm going to say 60 times by 10 to the power of negative 6, then plus 400 times by 10 to the power of negative 2 times by 10 to the power of negative 6. So if you, not negative 6, negative 4, if we look at this, we can take it back to its original form, because remember, if we say times by negative 2, we move the comma 2 back, then it's just back to that 4. So we've broken this 4 up into 400 times by 10 to the power of negative 2. All right. So if this is if this is a bit complicated, all that you remember is when you subtract 2, just add 2 zeros. Then you can write it as 10 to the power of negative 2. Okay, because that would then just bring it back to its original form 4. Okay, so now we can just simplify this. We still have this just hanging around until we work with it. Then we have 400 times by 10 to the power of negative 6. When I say add my exponents, minus 2 minus 4 gives me negative 6. So that's what I wanted. So now I can say this is like my variable, where we now have like terms, and we can add 60 plus 400. So that gives me 460 times by 10 to the power of negative 6. All right. So these don't change because they just add. And remember, like in the example, this is the same as saying 60x plus 400x, where if we add like terms, the variable doesn't change. It's just going to be 460x. And that's why we still have just to the power of negative 6 here, and not like negative 12 or anything. So to write this in scientific notation, I just have to have my comma after the 4. So I have 4 comma 6 times by, and I move the comma back 2 places, so that's 10 to the power of positive 2 times by 10 to the power of negative 6. So this then 4 comma 6 times by 10 to the power of negative 4. 2 minus 6 is negative 4. Okay, and then J, same here, have to add these two. Okay, and I need these two exponents to be identical. So I look at my biggest one between minus 3 and minus 1. My biggest one is minus 10. So to change my minus 1, so to change my minus 1 into minus 3, I have to subtract 2. All right. So that means this one, this 5,3, I need to rewrite as 5. I need to go 2 spaces forward and write it as 530 times by 10 to the power of negative 2, all right? Because I need that to the power of negative 2 to change it into a power of negative 3. So this has just been replaced with that. So let's just rewrite that. We've got 4,2 times 10 to the power of negative 3 plus 530 times 10 to the power of negative 2 times by 10 to the power of negative 1. In the next step, I'm just going to simplify that to look like this one. 4,2 times 10 to the power of negative 3 plus 530 times by 10 to the power of negative 3. Now I'm at the point where this is identical to this, and I can add my coefficients. So that's going to be 534,2, right? 530 plus 4,2 gives me this value, times by 10 to the power of negative 3. Then finally, this is write it in standard form. So now we can get rid of this. So now just think of it as, what would you do if you say 10 to the power of negative 3 is the same as dividing it by 1,000. When I divide, I move my comma back, and when I divide by 1,000, I move my comma back 3 spaces. So this is going to be 1, 2, 3. So this is going to be 0,5342. Okay, here we have K, and K is easy. That's just multiplying it out. So we have to put it in scientific notation. So first thing I'm going to do, I'm going to do this in one step. I'm going to simplify this part by multiplying the same basis as my exponents, and I'm going to change this one into where my comma needs to be there, right? So this is going to be 1,605 times by 10. Now think about this. We had a big number that we made smaller basically. So this has to be a positive 2, okay, times by 10 to the power of, so minus 4 minus 2 gives me minus 6. And then in my final step, I'm just going to say this base times by this base, add my exponents. So this is going to be 2 minus 6, which gives me 10 to the power of negative 4. Alright, so we are finally done, and that means we are at the end of the video.